So today's talk is by Mingcong Zeng from Utrecht University on real cobordism, its norms, and the dual steering algebra.
Okay, so let's start. Thank you for coming. And my throat is, I was a bit sick, so sorry if the voice sounds a bit weird. Okay, so first, this talk is about real cobordism spectrum MUR and its norm into C2 to the N. And all these guys plays a central role in the proof for non-existence of covariant elements, theta J, for J larger equals 7 by the famous paper Ravenel. And but the thing is, like, even though this spectra is very useful, we know very little about them. For example, the most fundamental question is, what's the homotopy group of the fixed point of this norm? They are completely unknown, except for MUR itself. So in this talk, I will give a new perspective of this spectra, especially in the easiest non-trivial case, G equals to C4, and explain why the computation here can be both very difficult and very interesting. This is the joint work with Lena Meyer. And we start with G spectra. So in this talk, G will be a finite group, usually a cyclic group of order 2 to the n. And a G spectrum is an orthogonal spectrum with G action. We will use the notation SPG, symmetric product, and S for the symmetric monadal category of G spectra. So one very important thing is, if you start with a G spectrum and you look at its various fixed points by various subgroups of G, there are natural maps connecting its homotopy groups. They are like restrictions and transfers. Restriction is something you can see in space, but transfer is something you can only see in equivariant spectra.
Mingcong, Stan, just to clarify, I just want to make sure what you're talking about here at G spectra. So you're not indexing by representation spheres, right? This is like the so-called night.
This is actually subtle. I'm actually talking about indexing by representation spheres, but I just want to give a very naive definition.
Okay. Okay. So you are talking about the so-called genuine spectrum.
Yeah, exactly.
Okay. All right.
Okay. So let's continue. So with all these structures between homotopy groups of its various fixed points, we can use G-Mackey functors to organize all these structures. So a Mackey functor, I'm using the most, say, handicraft definition because that's the definition I use when I actually do computation, is that given each orbit, you assign a Abelian group to it, and with all these structure maps, restriction, transfer, and while group action, and some compatibility conditions, I will just don't want to write down. And we will use MacG for category G Mackey functors. It's a closed symmetric monadal category with the box product, which in computation is kind of mysterious to compute, but well, it's there. And the homotopy groups of G spectrum X and its fixed points, it forms an integer gradient Mackey functor. We use underline for every Mackey functor. The most important thing is that pi 0 of the sphere spectrum is the Bernstein Mackey functor A, which is actually the tensor unit in the category of Mackey functors. And in computation, we really write Mackey functors in ways of Lewis diagram. A Lewis diagram of C4 Mackey functor just looks like this. We write the C4 over C4 level on the top, and the C4 over C2 level on the middle, and the underlying level on the bottom, with restrictions going up, going down, transfer going up, and while group action will be indicated by G module structure. And then we talk about representing spheres. So if we start with a orthogonal representation, then you take the one-point compactification, you actually get a sphere with G action by something like rotate like this. So this construction extends to all virtual representation, and you can talk about a representation sphere of anything in ROG. And so if you combine these two together, given a G spectrum, you actually obtain an ROG graded Mackey functor out of it. So the most important representation is rho G, the regular representation of G. So the first thing people want to do is that, like classical theory, you want to build element Klein spectrum from a Mackey functor. So this can be done. And there's a very subtle thing here is that the axiom of element McLean spectrum only controls the integer gradient homotopy functor, but not RG graded one. So that means given an arbitrary representation, it's RG graded homotopy functor of an isotope clean spectrum can be highly non-trivial, and it turns out it's very essential for the future computation. And the next important guy here is the real cobordistan spectrum. The complex cobordistan spectrum is built out of the Thom space of the tautological line, of the tautological bundle over certain Grassmannians, and they actually comes with a natural C2 action by taking the conjugate complex bundle. So this will give MU a C2 structure. We call it MUR. And if you localize that too, it's just really like MU, it splits into wedge of suspensions of BPR, the real Brown-Peterson spectrum. And if you start with a C2 spectrum X, you can take the norm by smash itself many times and using the action, which is like from you move the first guy to the second, you move the second guy to the third, you move the last guy to the first, but twist with the C2 action on X itself. That's a very naive definition of norm, but like that's the one which is convenient to write down. And of course, it should work if you have any finite group with a central C2 subgroup. And one thing very important is that the norm is the left adjoint of the Forgetto functor in the category of commutative rings. And if you norm BPR or MUR from C2 to C8, and you play like some very difficult game with them, and you can actually prove non-existence of covariant invariant elements. That's Hill, Hawkins, and Ravenel again. And we use notation BP C2 to the nth stands for the norm of BPR into the cyclic group of order 2 to the n. And these guys, they're actually related to the classical chromatic homotopy theory. Because on the other end of the spectrum, if you look at Morava E theories, there are various cyclic subgroups that if you look at the Morava stabilized groups, and they will contain various cyclic subgroups, and they give you an action on the Morava E theories. And this is the theorem of Han and Shi tells us when P equals 2, these two actions are actually comparable. And then you can norm it up to give you C2 to the n ring maps from norm of BPR to suitable Morava E theories. And you can actually try to compute on the left-hand side to get information on the right-hand side. So the first thing, if we want to understand BPR and its norm, is we want to understand their underlying homotopy groups with G action. This is done by Hill, Hawkins, and Ravenel. It tells you the following. So if you really fix the group first, then you can find this C2 equivariant elements. So this is kind of tricky because no matter how large your group is, these elements are always C2 equivariant elements, but they depend on the group you choose, and which they restrict to certain elements in the underlying level such that the underlying homotopy groups with G action are generated by all these VIs. So their definition is basically like, if you write down BPC 2 to the n as a C2 spectrum, there are 2 to the n minus 1 copies of BPR smashed together. And you can think about coefficients of the unique isomorphism from the first formal group law to the second. And it basically defines all these VIs. And one very curious thing is that if you look at G equal to C2, it gives you a set of generator of BP, which is neither Heise-Winkel nor Araki. And one very important tool in computing all this BPR and its norm is equivariant slice filtration. So you define a slice cell to be, you pick up a regular representation of a subgroup, and you take the representation sphere, then you norm it, then you don't norm it up, then you induce up to G from a subgroup H. And this will give you a so-called slice cell. And you use them to build a localizing subcategory of G spectrum. It's called the n-slice positive category. And then you can define box field localization, it will be an equivariant analog of the Postnikov tower. in the non-equivariant case. In non-equivariant case, you can just copy this construction and you actually got the Ponsonkov's tower. So that means the slice tower or the slices, if you forget all the group action, it will simply give you Ponsonkov's tower and the Ponsonkov's sections of your underlying spectrum. And one very important thing is that we actually know what the slices of BPC2 to the n. So a theorem of Hughes-Hopkins-Ravenel tells us the norm of BPR into C2 to the n, the slices they are all known. They are algebra over the associated greedy objects. It's an algebra over the element MacLean spectrum of the constant Mackey functor of integers. But I need to explain a bit about notations here. So for example, if your G is C4, then the 0 slice will be HD itself. 2 slices, it will be something induced from C2. You will be, if you start with the C2 HD, then you suspend by row 2, then you induce from C2 to C4. That's your 2 slice. And the generator is V1 and the gamma V1, which is the conjugate by the C4 action. And the 4 slices, the first thing you see is you will see a non-induced 4 slice. It's given by row 4 suspension of HD. And also you will see induced 4 slices. It's given by, again, the same construction as 2 slices. And the generator is V1 squared and gamma V1 squared. And by knowing the slices, we can try to understand the slice spectral sequence. So notice that the first thing very interesting is that the construction, so the first thing very interesting is that this theorem tells you pi 0 of BPG is actually Z instead of A. So this is very interesting because if you, in the end, if you want to compute the slice spectral sequence and you resolve all these differentials and you come into the extension problem, you realize that you're actually doing homological algebra not in the category of Mackey functor, but in the category of Z modules, which turns out to be way easier than doing homological algebra in Mackey functors. And the slice spectral sequence has E2 page of the following form. It will basically be the algebraic greedy homotopy Mackey functor of the associated greedy objects. And so, if you want to know the E2 page, you need to compute the algebraic greedy homotopy Mackey functor of HZ. And this can be done by Seldon method, which is not really hard, but it's just a lot of information to be organized. And I learned this principle from Doug, is that when possible, you really want to compute the slice spectral sequence as an algebraic spectral sequence of Mackey functors, which for many people, it seems like unnecessarily complicated, but I will explain why. So the first thing is we want to use algebraic grading because the most important elements, they're just not in integer degrees. So these 2 families of elements are very important. The first family is it's an A family. So if you start with a representation V, you take its representative sphere, that means 1-point amplification, you can always embed S0 into them by sending 1 point to 0, another point to infinity. Right, that's if you look at the sphere, it's actually like 1 to the south pole and 1 to the north pole. If you think the G rotates it in the middle, that's the A element, and the V element is that if V is an orientable representation, you can actually find an equivariant element in the correct degree, such that the element will forget to the degree map of degree 1 in pi 0 of HD. So that's our UV. And because AV comes from Fourier image, it's always a permanent cycle in the slice spectral sequence. It lies in the filtration, the degree of your representation. And UV, they are always filtration 0, and they always support differentials in slice spectral sequence of norms of BP. And this theorem is very tricky. It explains to you why you want to use Mackey functor. Is that actually in these spectral sequences, all the extension problems are automatically solved if you understand all the differentials in all the algebraic grading. So this is very tricky. The actual form of the theorem is pretty long and technical. I don't want to show it, but this is the philosophy in the computation, is that if you feel like there should be an extension happen somewhere you are interested in, you can always go into another algebraic page, computing differentials there, and that will automatically tell you whether this extension happens or not. We will see some examples later. So that means if you compute slice spectral sequence as algebraic spectral sequence of Mackey functors, you can keep track of the whole multiplicative structure and all the extensions, all by this is super convenient. So first, we start with some slice differentials. We start with theta to be the sign representation, and we use rho G bar to be rho G minus 1. Like you just remove the invariant part from it. So Hughes-Hopkins-Ravenel tells you there's a family of differentials, looks like the following, which kind of complicated, but it is what it is. And this tells you a very small amount of differentials, because in slice spectral sequence, all the UV supports differentials. But this only tells you a single family. It's like U2 sigma to the powers, what their differentials look like. It turns out to be the, say, the cleanest part of the slice spectral sequence. When G equals to C2, this theorem reads like D3 U2 sigma is V1 A sigma cubed, D7 is V2 A sigma to D7. It turns out in this case, it completely describes slice spectral sequence of BPR. So now we focus our attention to G equals to C4. So let sigma 2 be the C2 sign representation, sigma is a C4 sign representation, and there's one extra representation, which is C4 acting on R2 by rotate by 90 degrees, like this. So the first step is, we really want to understand all the underlying C2 slice differentials by using the unit map from PPR to the underlying C4 spectrum of BPC4. So under this map, AV goes to AV, UV goes to UV, but one tricky thing is like, what's the image of VIC2 in terms of VIC4? So again, this is done by Hughes-Hopkins-Ravenel in another paper, is that using this, we see the first one is easy, V1C2 will go to V1C4 plus gamma V1C4, basically because V1C2, you will be, so basically this is the only place it can go. But it turns out V2C2 will go to something quite complicated. The formula will get messy very quickly, but we don't need their full forms to compute all differential because when we look at the spectral sequence, targets of higher differentials are always in the quotient of lower differentials. So that means we only need the formula of VIC2 in terms of VIC4 modulo lower VIs. So this leads us to the first theorem. It tells you if you modulo lower VJC2, then VIC2 has a relatively simple form. And so that means we understand all the C2 slice differentials in BPC4. They look like what you expect, and this completely describes the C2 slice spectral sequence of BPC4. And this formula might look like familiar to you because in dual stereo algebra you have this identity which describes how you compute Xi bar from all the Xi's inductively. I mean. And actually the proof is not that hard. The only thing you want to show is that all these VIC4, remember, they are actually C2 equivalent elements. You want to show that VJC4, if you take the C2 geometric fixed point, it becomes Xi, and the gamma VJC4, it takes geometric fixed point, it becomes Xi bar. Then you know if you make this combination, the geometric fixed point will be 0. So that means it will be killed by a slice differential if you multiply by powers of A sigma, and that's how this theorem is proved. So this is purely algebraic, but can we go deeper along this line? So the first thing you notice is that so this is kind of tricky, but if you really don't stay in the integer degree, if you go into an algebraic grading, the algebraic grading will be some integer minus n lambda for n larger than 0, and the integer is less than 2n. You realize that there in the C2 level, everything else is gone. Only the part which looks like dual string algebra will survive as a C2 module. The C2 acts on this by the while group action, and on the other side is by conjugation on dual string algebra. So this is the picture when n equals to 2. And this is the E2 page of slice spectral sequence with all the differentials. And this is the E infinity page. So the red circle part is actually isomorphic to dual string algebra, but the problem is like if you start with here, if you start with total degree 0, then on lower filtration there will be extra things appear to make things more complicated. But if you let lambda goes very large, then this part will get longer and longer, and you get a larger and larger part, which just looks like dual string algebra by the previous theorem. So the first idea to exploit it is that you can try to build some kind of something looks like the homotopy orbit spectral sequence, but feed in the information, not the underlying part, but the C2 equivariant level with the while group action. This is actually done by the isotropic separation sequence. So if you look at the isotropic separation sequence here, where the S parenthesis infinity sigma is the unit sphere of the representation infinity sigma, and you add an extra base point. And you realize that the third term is actually super easy. It's simply the element McLean spectrum of the easiest non-trivial Mackey functor you can find. And the first term is something computable. You use the cellular structure of S infinity sigma plus, and then there will be a spectral sequence computing that, and its E2 page is actually isomorphic to the homotopy orbit spectral sequence of FF2 symmetry F2 when in a certain range. The range is the same, like exactly in this range. So you might start wondering, so maybe they are actually the same. And the answer is yes. It's not the same as E2 page of some weird spectral sequences. Is that the answer is actually the same. So, but it's like, but the cause is like you actually end up in a very limited range in a very weird algebraic page no one care about. But we can actually move back to talk about BPC4 itself. So the main theorem of this talk is the following. I think I'm going a little bit too quick. So if you have any question or I'm just rushing too fast, you can really interrupt me and ask. So the main theorem is that if you start with the easiest C2 Mackey functor possible, which is the C2 Mackey functor, and its C2 over C2 level is 3 over 2, and the bottom level is trivial, and then you have an equivalence. If you start with BPC4, you try to invert the element A lambda. Remember, the element A lambda is the element where its element comes off which image, where A lambda is like you start with S0, 2 points, you embed it into S lambda by North and South pool. It gives you something. It gives you the map of space. It gives you the map of spectrum. It gives you a permanent cycle inside of any C4 spectrum. If you invert that, what you get is you get the norm from the element McLean spectrum of this C2 Mackey functor into C4. And more interesting is that if you take the C4 fixed point, the genuine fixed point of this norm, you will get the C2 homotopy fixed point of HF2 symmetry F2 with the conjugate action, or the swap action, swapping these two factors. So the first part is proved by comparing geometric fixed point. The second part relies on the following very magical theorem, is that the Tate fixed point of HF2 symmetry F2 and the conjugate action is actually HF2 itself. So this theorem is more general. I think the most general form I know is that if you start with any spectrum bounded below, if you take its p-fold symmetric product and you take the CP Tate fixed point, you will get its p completion. But anyway, here we only need a very specific version. So that means if you really want to understand BPC4, you try to understand this, And then you start to you end up with this weird object, which is HF2 smash F2 with conjugate action, and you try to take its homotopy fixed point. And what can we do? First, we can fit. So first, we can fit our objects into the Tate diagram, or more precisely, the first row of the Tate diagram. And by this, the first object can be computed by the homotopy orbit spectral sequence. And if you really carefully move into algae grading, and if you try to compute the algae graded homotopy orbit spectral sequence here, you realize that if your star is small enough, there will simply be nothing there. So that means there will be nothing in the first term. So that means the last term actually computes what you really want, the norm of BPR into C4. But this, of course, only works in the same range. So that means if you really want to understand something in BPC4, you can try to understand this guy through its Tate spectral sequence, or homotopy fixed point spectral sequence, or homotopy orbit spectral sequence. So, but this is a super difficult topic because it's very—
wait, this is Danny.
yeah.
Can you go back a slide? Can I ask a question?
Yeah.
So in the corollary, the left-hand side, there's an n there, right?
Yep.
And for the right-hand side,
there's no n. Yep.
There's no n.
Yep.
So it's a correlation. So does that mean I can plug in any n for the left-hand side?
But for left-hand side, you need to be careful. Our star depends on n. So that means
star depends on n. Okay.
Yeah. So that means when your n is larger, you will have a larger area, which this corollary is correct.
Oh, okay, gotcha.
And that area is precisely the part where everything is not annihilated by a lambda.
I see. Okay, gotcha.
Because if you multiply by a lambda on the left-hand side, you actually increase number of n by 1.
Yes.
Yeah, so that's basically the idea. And that's actually why it's independent of n on the right-hand side.
Okay. All right. Thanks.
Yep. Okay, so one very naive attempt is to compute the Tate spectral sequence of this guy. This spectral sequence is super strange. It has a huge E2 page because you can literally write down dual Snowy algebra and look at its conjugate action and figure out what's the C2 module it is, and take the Tate cohomology, and they will be your E2 page. But only the class at 0, survives. So everything kills everything in a very weird fashion. And Brunner computes its E2 page up to 200 stem by a magma program. And basically there's no clue, no pattern what's going on there. Like a computer can compute up to a certain range by a certain amount of time, but for me personally, I don't see any pattern. So its E2 page and differential, they are difficult or at least very weird. So this is a picture of the first few stems of the E2 page. So as we can see, you start with 1, C1 square. There's no C1Q because there's a formula tells you C2 bar is C2 plus C1Q. So that means in that part is a free C2 module, so it has no Tate cohomology. Similar thing goes on with the next degree, until here, you have a new generator, which named C1 cube, C2 plus C2 square, and in degree 6, and in degree 9, you have one more. And everything generates all this whole line of 0/2 everywhere. And so it's very difficult to imagine how everything kills everything. Only this guy, right in the middle here, survives. And the next picture is a small part of the homotopy orbit spectral sequence, which amounts to this lower part. And I draw some differentials and some extensions. For example, there's these differentials from here to here. It corresponds to differential from here to here. And above it, there's an extension, and also here to here. Above it, there's another extension. But it's but in general, this kind of thing, it's very hard to argue. It's very, like every differential is a struggle. Every extension, I don't even know how to prove this in this spectral sequence. But we will come back with more tools later on. So as you can see, the homotopy fixed point spectral sequence is multiplicative, but it's not locally finite in E2 page. What I mean is that if you look at the homotopy fixed point spectral sequence, you go above, you can count infinitely many of 0 over 2 in E2 page. So you don't have a nice approximation or a nice guess about how large the infinite page will be. And it has like tons of differentials. If you look at its homotopy orbit spectral sequence, it's not multiplicative, but it's indeed locally finite, and it has lesser differentials than homotopy or fixed point spectral sequence. And all the differentials in Tate spectral sequence, which cross the x-axis, representing elements, kill each other by the norm map. So that means, for example, you have a differential from this element to this element. And what this represents is that in pi 0, the homotopy orbit spectrum is 0 over 2. The homotopy fixed point spectrum is actually 0 over 4. There's a hidden extension here. And the Tate spectrum is 0 over 2. So that represents this non-trivial map from 0 over 2 to 0 over 4, again, to 0 over 2. And all the longer differentials crossing this x-axis will do the same thing. It represents elements killing each other from homotopy orbit to homotopy fixed point. Remember, the Tate spectrum is super easy. It only has a single non-trivial pi 0, and all the other pi star, they are trivial. So that means everything must kill everything almost by this norm map. So if both are very difficult, can we find a way out? So how about the slice spectral sequence of this guy? But this is kind of very desperate attempt, because we know slice spectral sequence is actually isomorphic to homotopy fixed point spectral sequence in a very large range. This is the theorem by John Illman. But we have one more tool in our hand. If we know the A lambda inverse of BPC4 is the norm of this guy, and the C4 fixed point of the norm is actually the homotopy fixed point of C2 smash C2 with conjugate action, that means that we can try to look at the A lambda inverted slice spectral sequence of BPC4, which will actually compute this very strange object. So the E2 page of A lambda inverse slice spectral sequence of BPC4 is A lambda inverse of all the slices. It will be HD with C4 with the norm construction on all these C2 elements. So one important thing is that if you invert A lambda on HZ, its algebraic homotopy functor is actually not hard to compute. It's somewhere in my thesis, and I did that for different purpose. But in the end of the day, it actually gives you a multiplicative spectral sequence of ROG gradient Mackey functors, which is locally finite E2 page. So before we actually dive into that spectral sequence, we need to introduce some notations, because there will be a lot of Mackey functors there. And we use circle for this 0 over 4, 0 over 2, and different triangles for 0 over 2, 0 over 2 with different restriction transfers, bullets for a single 0 over 2 on the top. And I will use this bullet hat for the induced Mackey functor from 0 over 2. And bullet bar with the Mackey functor 0, 0 over 2, 0. Okay, so on the left-hand side, we have the E2 page of the A lambda inverted slice spectral sequence of BPC4. On the right-hand side is the E infinite page. Very interesting thing is that this E2 page is actually it's very easy to describe, and it's very interesting. So above the zeros, above the x-axis, it really looks like the slice spectral sequence of BPC4. What you can think is that if you just ignore all the bottom guys and you replace everything infiltration 0, from the everything there, they are kind of torsions. If you replace them by the corresponding torsion-free guys, you actually get slice spectral sequence of PPC4 back. And another thing is that there are various vanishing areas. For example, in the below, you have this vanishing line of slope -1 down here. And here you have a vanishing line of slope 1, where above this area, everything becomes super easy, and all these very massive guys only appears between slope -1 and 1. And there is this line of slope 4. Sorry, I think it's slope 3. Above the line of slope 3, there's simply nothing there. And what's very interesting is that in this area, where things are very easy, all the differentials are very easy to describe. They are Hughes-Ravenel C4 differentials. But in this area, there are really a lot of things going on. I don't want to write down all the differentials because they are very complicated, but I can tell you the patterns, the basic patterns. So first, what you will encounter is you will encounter D3s. For example, there's a D3 from this guy, infiltration -2 in stem 3, hitting this guy. So this is the result. You have a bullet here. You will have a bullet bar here. That's the result of D3 differential. And this D3 differential just goes on diagonally. There's a one D3 from here to here, 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 and it goes on. It basically cancels out everything here, and it kills a large portion of everything here. The same differentials happens. A D3 from here to here, from here to here, and it going all along this line. And it just repeats forever on D3. Like these adjacent lines, they mostly not cancel each other, but the line below kills a large portion of guys. And what remains in what remains in C2 level is basically you identify V1 with gamma V1. So that's why you just kill so many guys. And then there will be D5. There are two different kinds of D5. The first kind is a Hughes-Ravenel D5. You first witness here, from this circle, kill one of these bullets here. There's a D5 from here to here, and it moves on. It moves on by the slope of 3. For example, there's D5 from this 2 kills this 2. A D5 from this 2 kills this 2. A D5 from this 2 kills 2 of 3s. There's one guy remaining, and you can see this one guy remaining is actually here. No, it's actually here. It's actually here. This is the guy remaining, and 3 kills 4, and this guy remains here, and it goes on and goes on. And there's another kind of D5, starting from this guy, kill this guy. And then you will see D7 from this line kills things in this line, and it goes on and goes on. It's very difficult to describe all the differentials here, but in this range, if you look at stem from 0 to 7, which is actually a lot, it corresponds to things here, you actually know all the differentials by very ad hoc method. And this is the E-infinity page. What I want to point out is that there are two kinds of exalted extensions of Mackey functors. The first kind is I use the purple color here, which means this element, remember in the picture here, this guy, it has a non-trivial C4 over C2, but it has a trivial C4 level. This guy supports a transfer from here to this element, to this bullet. So that means this guy supports an exotic transfer from here to here. And this blue line means this guy here in the negative filtration supports an exotic restriction from this guy to the C2 elements. So that's the inverse story. So that means this guy here in the negative filtration supports an exotic restriction from here to here. So basically what I want to say is that if you only look at the top part, you will see this Mackey functor with a transfer. If you only look at the bottom part, you will see this Mackey functor with a restriction. But when you combine them together, these two Z over 2 actually have a non-trivial extension. They become a Z over 4. Why? Because if you restrict, then transfer, then what you will get is you will get twice of the element you start with. That's a part of axiom of module over the constant Mackey functor Z. So that means even for in every single part of this, you only see a non-trivial extension of Mackey functors, but you combine them together, you actually see a non-trivial extension of abelian groups of filtration 8 from this guy to this guy, which if you don't care about Mackey functor, if you care only about the C4 fixed point, it's very difficult to argue about, but it's very obvious if you look at Mackey functors. And yes, these two extensions, they are all caused by differentials D5 in different algebraic page, which is like very standard to argue about. And similar things happen here, but where you have two different extensions of filtration 14, and again in the C4 level, it becomes non-trivial extensions of abelian groups. And there are some trivial extensions. For example, here. If you look at C4 level, you have Z over 2 and Z over 2. It's a possibility that it becomes a Z over 4 in the end of the day by some very mysterious non-trivial extension. But if you look at Mackey functors, you realize this is actually impossible because you can actually compute the Mackey functor x1 between these two Mackey functors. And you simply realize that the x1 is 0. There's no Mackey functor extension between these two. But there can certainly possible to be abelian group extensions, but that means there's no way these non-trivial extensions of abelian group fit in the whole structure of a Mackey functor. And similar things here, you can make similar argument to show that this extension can never happen. And so if you combine all of this together, you can actually compute some very funny things. You can use this spectral sequence to compute the first few stems of HF2, symmetry HF2 with C2 homotopy fixed point. And you realize it's 0 over 4, 0 over 2, 0 over 4. Like, go back, 0 over 2 plus 0 over 2, 0 over 2, 0 over 2. And here you see a 0 over 4, which is a very super long extension. But with this 0 over 2, and you see a 0 over 2 plus 0 over 2. But in Mackey functor, they actually represent very, very different things. And you actually, one more interesting is that you actually see the multiplicative structure. For example, here, you see a 0 over 4. And here you see a 0 over 2. And here you actually see this guy is actually this guy square. So if you call this x, it will be x squared, and this will be x squared divided by 2. But here, unfortunately, this is not x cubed, because you look at this element, this is norm of V2 something, this is norm of V1 squared. X cubed is actually killed by a slice differential, but norm of V2 actually survives. And the funny thing is like the square of this guy is actually here is again twice of something. But again, the cube of this guy is actually killed. And this element is not this element times the element in stem 1, it's a whole new guy. And its square actually survives. This part is easy to compute, its square actually survives. So you got this many multiplicative generators where their square survives, their cube doesn't. And any multiple of between these two, they are just 0. And then from here, you start to see complicated phenomena of things in the middle, and this will just grow bigger and bigger. Because remember, the C2 underlying of this guy will resemble the dual Stingray algebra itself, and the F2 rank of that will just grow. So you expect to see more and more complicated things down here. But the point I want to make is that first, in this range, all differentials can actually be read from Hugh Shi-Wangshi's computation of BPC42. It's very funny. It's like you just basically copy and paste all their differentials, and then you invert a lambda, and that's all the differentials you need to compute this spectral sequence. At least for a very large amount of range, I think up to stem 15 or something. But it really gets more and more complicated in the middle. So it's a really heavy labor work to write down all the pictures. But this part of the computation is actually not new. You can read them from there, but you compute something different, quite different. And all the non-trivial extensions, as I said, they are proved by RG gradient Mackey-Functor structure. And one more thing is that in this spectral sequence, all the underlying C2 level differentials, they're actually known. They are D3, D7, D15. That's our first theorem. So that means you already know a lot about this spectral sequence. You know its E2 page, you know a huge chunk of its differentials, and you can try to make arguments along like how the Mackey-Functor structure and the multiplicative structure and the norm to see what's going on in the C4 level, and this will actually tells you something very rich, and it computes F2 match F2 with C2 homotopy fixed point. The last thing I want to remark is that in the range I already compute, I think it's true in general, but I don't have a solid proof. I don't have a solid statement yet. Is that if by some miracle you understand HF2 match F2 with it's the two homotopy fixed point, and in turn you understand this spectral sequence, you can recover the slice spectral sequence of BPC4 by doing the following. You just ignore everything below filtration 0. You change everything in filtration 0 from this torsion Mackey-Functor to their torsion-free counterparts, and everything which is killed by things from below becomes a permanent cycle. And then you actually recover BPC4, the slice spectral sequence of BPC4 in this way. In the range I actually compute up to something like stem 15, there's no problem in doing that. I think this is true in general, but it's kind of difficult to make a statement out of it. So that's the end of my talk. Thank you. Sorry for speaking so quickly and.
All right. Well, let's thank him first of all. Okay, and I'm going to go ahead and mute everyone just for a second. Okay, and do we have questions for Mingcong?
I have a question.
Mm-hmm.
So for the last part of your talk, you talked about using the computation for the HF2 smash HF2 with the swap action to recover BPC4, right?
Yeah.
So are you saying that if I know the left-hand side slice spectral sequence,
yep,
the slice spectral sequence with A lambda inverted, then once I know how the differentials work there, it will be relatively formal / straightforward to recover the slice spectral sequence for BPC4?
In the range I compute, they coincide, but this is not a theorem yet. I know. Okay. I think I can explain a little bit more because I mean, you know, there's a certain D11. It coming from something looks like a lambda torsion hit another A lambda torsion.
Right.
But the thing, I thought it last night. It's that the problem is that when you see it, it's actually a lambda torsion, but that thing only becomes a lambda torsion after D15 page. In the 11 page, it's actually not a lambda torsion. So that differential can be actually seen in this A lambda inverted spectral sequence. I can tell you where it is. Where it is? It's something. Yeah, it's something. It's something like. I think it's something like. Where is this guy? Yeah, you see, this bullet bar. It hits one of this. It becomes a triangle upside down, and this guy supports a D7. And its D7 target supports a filtration of exotic transfer of filtration 4. So this guy, so there's one mysterious transfer here supports a D11 hitting one of this.
Oh, I see. So you're saying on the D11 page, they're not A lambda torsion yet?
Yeah. There's a certain D11 happens somewhere.
And at the moment it happened, neither of them are A lambda torsion.
Right. Neither. Yeah. At the moment it happened, neither of them are A lambda torsion. So you actually see that very weird differentials in this A lambda inverted spectral sequence.
I see. Okay. All right. Thanks.
Other questions? Okay, if not, I'll unmute everyone and we can thank Mingcong one more time. Okay, and again, a reminder, this was our last regular seminar for the academic year, but there will be a mini course, 4-hour mini course in May, starting May 14th by Agnes Baudry. Check the website and I'll send out an email announcing that. Okay, thanks everyone. All right, thanks Mingcong.
Yeah, thank you.
Yeah, that was like, there's a lot of material.
Yes, I'm very sorry for the rough picture.
Yeah, well, no, the pictures are great. It's just like amazing that you can kind of keep track of all these details and like, you know, so much of this is like, you know, I see, for example, there's like this graphical calculus, right, that you have, right?
Yeah.
You know, the hats and the lines and the slashes and so forth that really kind of helps keep track of what's going on.
Yeah, I mean, computing in Magefunction is something like very weird. Like definitely Doug did that, and Doug really loved that.
Yeah.
And he tried to convince everyone to do that, but yeah, I mean.
Well, it carries a lot of information, right? So, I mean, you know. All right.
That was great talk. That was really fun. I like those long extensions, those double extensions you have. Those are really, really interesting.
I mean, I learned that from you.
Yeah, it sounds familiar, but you're taking it to another level. It's nice to put that in the Tate spectral sequence.
Oh yeah, I mean, this is not the Tate spectral sequence. But the thing is, like, this actually tells you this extension actually tells you way back there. Here, these two extensions, no one. I don't know anyone have any arguments about. I didn't even know they exist before I compute the slice one. I didn't even know this kind of extensions they exist. Yeah, but yes, they are there, and it's very strange.
Yeah, it's very cool.
Yeah. Yeah, and this is actually a continuation of the thing I keep talking to you, like when we were in Cambridge.
Right.
Yeah, because at that time, like I think I'll do a string algebra, but I didn't know, like, yeah, Leonard has this great idea. Leonard has a great idea, like about what the main theorem should be. Yeah, and then we follow up, and then we follow this line, and we end up here right now.
Okay. Well, it's really nice stuff. I really like it.
Yeah, thank you. Yeah, I'm glad you like it. That's the